Continuando con el programa, vamos a presentar ahora la siguiente charla. Eh, la siguiente charla está a cargo del doctor Martin Makler. Voy a hacer primero una presentación sí, voy a hacer una pequeña presentación de frente en español y luego la voy a hacer en inglés. Pido una disculpa por mi pronunciación. El doctor Martin Makler es El doctor Martin Makler es investigador del Centro Internacional de Estudios Avanzados en Argentina y también del Centro de Investigación de Física de Brasil. Tiene intereses de investigación en lentes gravitacionales, clúster de galaxias, materia oscura, energía oscura, y el día de hoy nos va a presentar el tema titulado Anillos de Einstein eh, como una prueba cosmológica. Ok, ahora voy a hacer la presentación en inglés. I apologize for my English pronunciation. The following presentation is that of Dr. Martin Makler, researcher at the International Center of Advanced Study in Argentina and Brazilian Center for Physics Research. His research interests are gravitational lensing, cluster of galaxy, dark matter, dark energy, and today he presents the topic entitled Einstein Rings as Cosmological Proofs. Doctor, our space is yours. You could give the talk in English, so that is to understand by all present. Thank you so much. Okay.
Ok, buenos días a todos y a todas. Good morning to everyone. Actually, I was told to speak in Spanish so that most people would understand. So just to make it clear, if it's the case, I apologize for English speakers, but I can take questions in English. Ya había entendido que me habían pedido para hablar en español para que sea más accesible. ¿Sigue siendo así o prefieren que hable en inglés?
Dada la situación actual, sería una preferencia que sea en inglés, doctor.
Ok. Entonces pido disculpas a los hispanoparlantes porque voy a hablar inglés. Y bueno, de cualquier forma, los slides están en español y por supuesto pueden hacer preguntas en español y bueno, hablaré en inglés. So at the end, I will speak in English, although my slides are in Spanish, so I hope everyone can follow. So thanks a lot for the invitation. It's a pleasure to be here. I mean, I would prefer to be there in Callao, for sure, but given the situation, I'm happy that you're holding this meeting, so thanks a lot for the invitation. And I hope in another opportunity I can visit Callao. I mean, Peru is a fascinating country, and I would be glad to be presently in your university in the future. Okay, so thanks a lot for the introduction. I can skip this, and I would just like to remind, are you seeing my slides changing?
Yes.
Okay, great. So before I start, I would just like to quote this from Carl Sagan. There are no stupid questions. Each question is a cry to understand the world. So please do not be shy. Unfortunately, we have just 35 minutes, so I will not be interrupting to get questions, but please keep the questions to the end and ask any questions. This talk is for anyone, and so don't be shy. Sometimes the question that seems more basic is the most complex and the one for which we don't have answers. So do ask a lot of questions. To start with, let's try to understand, the talk is about gravitational lensing, and gravitational lensing starts with the bending of light by gravity, which really, as we see it today, started with the general theory of general relativity from Albert Einstein. So in 1905, as you know, Einstein proposed a special relativity, and that makes a huge change in our understanding of space-time and dynamics. In particular, space and time are not separate now. They become part of a four-dimensional entity, which we call Minkowski space, because Minkowski was the mathematician that actually shaped a special relativity in a very nice mathematical way, very appealing statically and mathematically. So Minkowski was a mathematician. And I like to quote this sentence from him that he says, "The visions of space and time that I'm going to present here, they come from experimental physics, and from there is strength." So you see, a mathematician is saying that the strength of the theory is not because it's beautiful mathematically, but because it represents the real world through experiments. And that's the power. Okay, so already in 1905, Einstein derived this very famous equation, E = mc squared, and already he can think that since everything that has mass gravitates, since light has energy, then maybe it gravitates because there's equivalence between mass and energy. So as soon as 1907, Einstein started thinking about this. He thought about the equivalence principle. And in 1911, he obtained the first equations for the deviation of light, what we call gravitational lensing. But still his theory was not complete. And in 1915, his theory was fully complete. He obtained the double of the deviation that he obtained before. But that's what we use until now. There may be differences, as we will see at the end of the talk. But the basic idea is that space-time is curved, and light will make not a straight, but a curve in space-time, right? And we can everything that exists should gravitate. That's the bottom line. Okay, so let's go to gravitational lensing. It's a consequence of the bending of the light by masses. So again, we show this picture where you see space-time is bidimensional in the top right, and there is something like the sun there that's making deforming space-time, and light makes a curved path. I don't know if you see my mouse. Actually, I don't see my mouse. Anyway, so in the left you see a plot that shows a cartoon that shows a cluster of galaxies. So we are in our planet in one of the corners there, looking at the light that was emitted by a distant galaxy. But because of the curvature of space-time, this light can take several paths, as you see these curves. So the light can come from one direction, light can come from another direction, and we may see light coming from different directions. It means different images of the same objects. So because of the curvature of space-time, you see things like you see in the picture at the right. You see like yellowish galaxies. These are the galaxies from the galaxy cluster. And you see a blue thing. This blue thing is a galaxy that's behind the cluster. And you see multiple images of these galaxies because of gravitational lensing. So the galaxies amplify, is stretched, and you see several images of it. So the basic image of lensing is what you see there. Light is coming from a source called S. It gets close to the mass that we at a distance xi, and it's the path is deflected by an angle that we call alpha hat. So this angle alpha hat is given at the bottom. This is the result from general relativity in some limit that is important in this case. And from Newton, you get exactly the same result, but with a 2 instead of a 4. Okay, so there's a clear difference between Newton and Einstein, and the result of general relativity was proven observationally to be correct. So you know everything from lensing because of this picture, okay? So let's draw it again. We have a source of light in the right, a background galaxy. And we have a galaxy or a cluster of galaxies in the middle, and we have us observers in the left, right? If the source, the galaxy or cluster, and the observers, if they are very aligned, and if the mass of the cluster or the galaxy is very high, then you may see these strong lensing effects, multiple images, arcs, which are these galaxies that are bent by this curvature of space-time. And if you sit far from the galaxy, you will see a slight effect, which we call weak shear. Mathematically, we can understand everything on lensing from this equation that I'm showing. Beta is the coordinates that we see in the sky if there was no lensing. So it's the true position of the things is beta. And theta is what we see, the angles that we see in reality. So you can think of lensing as a mapping from beta to theta, okay? If you understand how one thing is mapped to the other, you understand everything about lensing. And the function that maps these two things is the function you see in the right, where there is these distances, DLS, the distance from the lens to the source, DOS, the distance from the observer to the source, DOL, the distance from the observer to the lens, and this gradient of phi. Phi is a potential, okay? So everything is coded there. These distances, these are cosmological distances, and they depend on the cosmological model, okay? I won't have time to discuss why, but we can discuss this later. But the cosmology is there in the distances. This potential psi is the integral along the line of sight of the Newtonian potential phi, okay? So this integral is what contains the information on the mass distribution of the lens. the potential phi, okay? So that's why in lensing we can have information from the lens potential, so from the mass of the lens, and also from cosmology. So this potential is like the Newtonian potential. It's given by the mass of the lens, okay? Good. So from one, in psi is like astrophysics, and in the distance is like cosmology, okay? So there are lots of phenomena associated with gravitational lensing. We can separate them by intensity. Like the strong lensing is what causes multiple images. It causes big distortions. And also, if you see multiple images of an object that varies with time, we will see a time delay between the images, a time shift. This thing oscillates, and then this one, and then this one. So there is a time difference between the different images. And all this has been measured, okay? And there is a weak effect, which is a slight deformation and a slight rotation that's also used very frequently in cosmology. Regarding the sizes, there are effects that are very small to see in an image, but we can see the effect of magnification. And this has been used to find new planets, to test dark matter models, to find primordial black holes or normal black holes, okay? There is a lensing that affects the images of distant quasars. Also, we see this by the magnification changing with time. And there is what we call macro lensing, that is an effect that we can see in images, like these arcs that you saw. So galaxies, galaxy clusters, large-scale structure, they produce macro lensing. And very recently, there has been new phenomena associated to lensing that has been observed, like the black hole shadow that you saw in 2017, 4 years ago. There is a lot of discussion on the lensing of gravitational waves and many other phenomena, okay? But today we are going to focus only on the strong effect, strong lensing, and also only in the limit of macro lensing, like galaxies and galaxy clusters. So I will show an example, pedagogical example about lensing by cluster of galaxies. And I will show you some very recent research we have been carrying on the rings on galaxy scale, okay? Just to check everything is okay, you can hear, you can see the slides?
Yes, doctor.
Okay, great. So just to recap, we'll be focusing on strong lensing, which produces these multiple images, big deformations, magnifications, and time delay, okay? And once we see these images, like multiple images, we can use this information to find what is the mass distribution of the lens. So it's like we can reconstruct the lens mass just by seeing the images. So it's like, in a way, we can see everything, even dark matter. Even if light does not emit, we can find what mass there is. That's why lensing is so important. Also, the lensing does not change surface brightness. It means that if I have an object that's small and then it's magnified by lensing, but it has the same surface brightness, so the total brightness is amplified. And the deflection does not depend on the wavelength of the photon, so it does not change the spectrum. So basically, we can use lensing as a gravitational telescope, and this has been used quite frequently. And so we can use this to study the structure of galaxies and galaxy clusters, and this helps us to place limits on like dark matter, how much it is, what it is distributed, the amount of baryons, and so on. And also brings complementary information on cosmology and tests of gravity, okay? I've been working in these two fields, but I'll only mention at the end some tests of gravity. And this is the diagram that you see at the bottom. And at the right, you see a very nice image of a system with gravitational arcs. But these images from the Hubble Space Telescope, they are not many. And most of the systems that today are like this that you see now. So these are very faint structures buried within the noise of the image and blurred by the sky, okay? Blurred by the atmosphere. So this is the kind of object that we seek to find and to use in our studies because they are more abundant. So that's challenging too. So some pretty pictures from the Hubble Space Telescope, where you see a lot of this effect of lensing. You see a very big arc at the right, but you also see some very small arcs all over the image. That's also a very nice image. We use some of these clusters to extract the cosmology, but this I will not address today. But I would like to show one example using these systems. That's another nice image from Hubble. But we would like to focus on one system. Next slide. I don't know why it's not going. Let's see. Okay, good. So I'll show this example of a system that we can model in a lot of detail and how this is connected to the scientific method. This picture that you see now, it's a galaxy cluster. So all these greenish galaxies are all together. They are part of the cluster. There is a lot of dark matter there. Actually, there's more dark matter than galaxies, okay? And what you see in the inset is a spiral galaxy that's further from the cluster, okay? And this spiral galaxy, it's a pity that I don't know why my mouse is not working. I'm sorry about that, but okay. Anyway, you can see in this picture, in the top left, you will see another copy of the same galaxy, is another image of the same galaxy. And very close to the center of the image, you see also two images of the same galaxy. So in this picture, you are looking actually at 4 images of the same spiral galaxy that's behind the galaxy cluster. And what is amazing of this system, as you see in the inset, is that there is a supernova, one star that exploded in one of the spiral arms of this galaxy. And this is the yellow thing. But you see 4 images of the yellow thing. Why? Because there is this galaxy that you see, this yellow galaxy in the middle of this supernova, which is also lensing the spiral arms of this galaxy. So you see 2 categories of multiple images. Multiple images of the whole galaxy, okay, the whole spiral galaxy, because of the big field of the cluster, and also 4 images very close by of the supernova because of one galaxy in the cluster. Okay, and you see the supernova, so you see 4 images of the same supernova. Why I don't see these images in the supernova in the other images of the galaxy, of this galaxy? Why I don't see it? Because of the time delay, because of the time shift. This supernova in the other images has already exploded or will explode. We don't know. So we didn't know. So, but we can make a model of this. So I will not go into details, but we can make a full mathematical model using the multiple images and reconstruct the density. And we can also reconstruct the time delay. So we can make a prediction. I'm sorry. So this is what is amazing, right? The idea of science in general, in physics in particular, is that we can make a prediction and test this prediction. If this prediction is correct, we'll see. And if we don't see what's going on, the prediction is incorrect. So it's a way to test our models. So when we make a model of this system, a full model of this system, we can predict if the supernova has occurred or will occur, okay? And there were several papers when this discovery was done, the discovery of the supernova in the spiral galaxy. There were several papers making predictions. So that's why we call when Refsdal meets Popper. So Karl Popper is this science philosopher that says that the theories must be falsifiable. So we must be able to prove a theory is wrong. That's a good theory. And Refsdal is the name of this supernova, which was given because he was an important person in gravitational lenses. Okay. So there were several papers. Here you see by a group of one of these persons was my former student. These people they predict that in the future. So this was 2014, when the supernova was discovered, and they predicted that one of the images will show the supernova at the beginning of 2016. Okay, and there were several other papers making predictions using models and using the theory. And they all agreed that in the future, in 2 years after that, you should be able to see this image, okay? So that's a very detailed model with a lot of images and so on. We can discuss in the questions. But this image of the supernova 2014, the prediction is that one image should have the supernova very long time ago. We didn't see it. There was no images of that quality at that time. The other also. But there was a window that the supernova should appear in the future. So people kept studying these systems, kept taking pictures of this system. This is 2011. We see no supernova there in the little balls. Then 2015, you see clearly the supernova, okay? 4 images of the supernova. And there is a prediction now that in the future, in this place marked site of SX, you would see a new image. A prediction of the time and the position also the magnification of that supernova. And in 2015, at the end of 2015, the supernova appeared there. So that's amazing, right? We are studying a galaxy cluster, which is billions of light years away. We are studying a galaxy that's behind it. We use general relativity. We use dark matter, which we don't know what it is, but we can make a model, we can make a prediction, and the prediction is seen in the data. I like to show the example because I think it's very important. It shows a lot of the strength of this field that has a predictable power, and it's also, of course, very nice, very beautiful, okay? So there is different people that predicted the position, and Grillo et al., this green one was the best, and happens to be the group where my student is, and so on. Okay, so that was just to show you one example. We also use this system to model the cosmology, but I don't have time to show this now, but we can discuss in the questions. So I want to have a lot of time for discussions, okay? So that's why I prefer to talk less and have more time for questions. So let's go to the Einstein rings, okay? So what is an Einstein ring? Einstein ring is an effect of gravitational lensing. In particular, when the lens is a galaxy, the source of the potential, the source of the light is a galaxy, the distance, like you see in green there, the source of light is a galaxy, and the source of the gravitational potential, the lens, is also a galaxy. So we call this galaxy-galaxy lensing. When they are more or less aligned, the image of the galaxy behind will have a shape of an arc, like you see in this picture, okay? So this an Einstein ring. We call Einstein ring this configuration, even when there is not a perfect ring. When there is a big arc, we will also call it Einstein ring. When you have strong lensing, galaxy-galaxy strong lensing, we'll call this Einstein ring, okay? So why this? There are several nice pictures. Of course, the nicest are from a Hubble Space Telescope. So these are some very nice pictures of Einstein rings. You see not all are really complete rings. Sometimes you see an arc, a contour arc, or a few arcs, but these are the systems we are interested in. And you don't need to make, the math is not complicated, okay? It's very simple math. If you are interested, I wrote an article in Portuguese for high school students and students in general of exact sciences in graduate school that have very simple calculations showing some solutions, including a solution of an Einstein ring. So the math is not complicated. But if you want to show this to your friends, for example, and then it gets a little bit more complicated, so what you can do is you take a glass of wine, the classical glass of wine, and in the bottom of the glass, this shape is produces a deflection of light that's very similar to the deflection of light of gravitational lensing. So really, when you look through the glass of wine, this glass part produces an effect that's very similar to gravitational lensing. So if you have like the source of light behind, you may see some multiple images or even a ring, okay? So you can show this to your friends, but do it before drinking the alcohol, because people will not believe you otherwise, okay? So, but as I said, it's very simple to model and so on. And so why are these things useful for? Will you give an Einstein ring to your partner? Well, maybe a picture, yes. But are they useful for science? For sure. As I stated at the beginning, they are useful to study the structure of the lenses, because we can map the mass, even mass that's not visible, like dark matter. We can study very far away galaxies because they are magnified. So we have this gravitational telescope effect. We can study distant galaxies that we would not be able to study because they were too faint. Also, we can put limits on cosmological models because of the cosmological distances. And I mentioned we did this with a big cluster from Hubble also. But all these things, they can also be done with other observables. Something that's also very interesting from lensing is that because of the curvature of space-time, the distances in cosmology, they don't sum. The distance from A to C is not the same as from A to B and B to C, okay? This not additivity of distances is very connected to cosmology. And we can measure that with lensing. That's a nice application. We can also use lensing to measure the expansion rate of the universe, okay, which we call the Hubble parameter. But all these things, in a way or another, you can also probe with different observables. Now, there is one thing that's very peculiar to lensing, which is the ability to test modifications of gravity. As you heard, the general theory of relativity is very successful to model these systems. But there may be little differences, little modifications on gravity, maybe at very large scales, that we want to test. In cosmology, we need dark energy, for example, to explain many things. What if there is no dark energy, but instead gravity is modified? So there has been a lot of work trying to test modifications of gravity. So in a general theory of gravity, for what matters for gravitational lensing, you have two gravitational potentials, okay? At the beginning, I told you about one potential, okay? Because in general relativity, there is one potential. But in general, you may have two potentials. So don't worry about the mathematics. This is just to show what we call a metric. And you see these two potentials, phi and psi, okay? In general relativity, phi equal to psi. But in modifications, they may be different, okay? So motions of galaxies, they are sensitive only to phi, only to the first potential, okay? Only for the time component of the potential. So if you test the motion of stars in a galaxy, you are testing phi. Now, lensing is sensitive to the sum of phi and psi, okay? So with lensing, we get the sum of the potentials. With motions, we had one potential. If we combine the two things, then we may set limits on the ratio, on the difference between the two, okay? So we'll call this difference gamma, okay? So gamma is the ratio of the two potentials. If we are in general relativity, then gamma is equal to 1. Other modifications of gravity may have gamma different from 1, okay? So if gamma is equal to 1, it is consistent with general relativity. It doesn't need to be general relativity. Could be other theories that have gamma equal 1. But if gamma is different from 1, then either you are making a mistake or general relativity is discarded. So that's why it's very interesting to measure gamma from the data. So we call this sleep parameter. And from now on, I will show things where we try to measure gamma, okay? How we do this? By combining, as I said, lensing, okay? In particular, these Einstein rings, and the dynamics of stars in the galaxies. How we measure this? We measure this from the velocity dispersion of the stars in the galaxy, and this is something measured by spectroscopy. We can discuss in the questions. Okay, so to make this test that I'm mentioning, we need to have systems of Einstein ring. Nowadays, there are about 200 confirmed systems of Einstein ring with models and with a lot of information. We were seeking to discover new systems. So we looked at galaxy surveys. We carried out our own surveys. So we applied for telescope time. We have images of some pieces of the sky. And we found new systems there. But also, very recently, when I say recently, like a month ago, 2 months ago, we did something that's even more simple. We use some spectroscopic information given by other people, other researchers, that found that there are two galaxies close by and aligned, and the one behind is magnified. And we say, and they of course say the same, this is probably a gravitational lensing. So let's look at images, at high quality images of these systems in imaging surveys. Sorry, and we found, we were looking to follow up some systems, which means that we were interested in getting Einstein ring system and study them in a lot of detail. In particular, Brazil and Argentina, they have time in a telescope called Gemini, which has an 8-meter mirror, so it's a huge telescope. It has a very sophisticated technology by which we can take images, and not only take images, but measure a spectrum in each little pixel of the image. And that's very useful for this modeling of the dynamics of the lens. So we were seeking to have candidates to observe them in detail with this Gemini telescope. So we looked at what we can do for next semester, and we found 22 new systems of arcs that we found 22 systems of art. Some were new, some were known, but we added information to those known too, and any of those could be used for our follow-up. So here are some images. You see they don't look as nice as in the images from the HST, but still it's amazing. You know, the central galaxy is the galaxy closer. The reddish or bluish ring is a galaxy behind that has been distorted by gravitational lensing. So we found a lot of systems. We applied for time to observe them in details, and I don't know what's going to happen. One thing we did also that was like 2 weeks ago is just a very simple example. Well, so in general, we want to have more of these systems, right? So we found some in the data, new systems. We got new data to find systems in our surveys, but also we were looking in catalogs, okay? There are systems that are candidates, but they need to have spectroscopy to be confirmed. So we applied for time also, not only in Gemini, but to do a very simple study of bright systems also with a telescope in Argentina named Casleo, okay? So we are now trying to get spectra of some system from Casleo and very detailed follow-up in Gemini. But we also said, well, you know, there's so many systems known in general, strong lensing. Let's take a database, a public database, that's a master lens catalog here, which has over 8,000 systems. And let's ask for the systems that had the information that we need. So we need the redshift of the source. It's a property from the spectroscopy of the distant galaxy. We need the redshift of the lens, and we need the velocity dispersion of the lens. And we found that there were a lot of systems with this information already ready. Okay, these systems had already a lensing modeling, so they were already an estimate of the mass from the lensing. And we took all the systems that are not too far. We call this a redshift. We can ask this during the questions, but the redshift smaller than 1.5. So that gave us 110 systems. So we just used these systems blindly in, well, there is a lot of math, but very simple math to derive this parameter gamma. And we derived, we made a statistical analysis and so on. And we derived a value of gamma that's surprisingly close to general relativity, right? With a 2% difference, okay, with an error bar that's about 2%. So that's quite surprising. That's also dangerous because, you know, when you study errors, there are the systematic errors. There are those that shrink when we get much more data, but there are also the systematical errors. Okay, statistical errors, it's easy. You know how to treat. They go away when you get a lot of data. But systematic errors, there may be an error in the modeling you're doing. So there may be an error in the kind of theory you're using. There may be an error in how you use the data. So they are very subtle things. And usually, when you look for something and you find what you're looking for, you just stop searching what can be wrong. Okay, so that's what we call a confirmation bias. But in this case, as we found a gamma that's so close to 1, we may be very happy we found what we assumed was the correct thing, which is general relativity, so we could stop, but don't. That's very dangerous for science. We have to look for every possible error that we may be doing, because maybe general relativity is wrong, and if we look carefully enough, we find that we stopped with gamma equal 1, but our treatment was not correct, and when we do everything very carefully, gamma is not 1. So that we are doing a big effort from theory to data, trying to really understand and understand the systematics to be sure that this result is correct, okay? Now, for this application and for other applications, we want to find systems, many systems. And these systems are rare, okay? There is one Einstein ring per 100,000 galaxies or per million galaxies, more or less. So they are very, very hard to find. They're very few. In the future, very near future, we will have surveys with about 1 billion galaxies, okay? About 1 billion galaxies. So we will want to search about 1 billion galaxies to find about 1,000 or 10,000 systems, okay? We cannot do this by eye. We have to make this automatically. And a lot of people have been working, trying to automate these searches. There's a lot of papers on that. Most nowadays use deep learning techniques, okay, machine learning techniques. And so there was a challenge, an international challenge, using simulations. So we know if they are rings or not because they were simulated. So there was a challenge to find these systems with simulations, and a lot of people entered this competition trying to find the systems in the data, but also trying to measure the systems. Instead of modeling the systems one by one, asking to the machine learning system to measure quantities like the velocity dispersion, like the Einstein ring, like the redshifts, okay? So the result came up last year of this challenge, and the group that won this challenge was the group at CBPF, was our group, with one of the deep learning techniques. So we were very happy with that because, well, we are able to find the systems, at least those in the simulations. But moreover, we are not only able to find, but we are able to measure these systems. And that's what is more interesting. And that's not, there are fewer results in the literature doing that, okay? So this is the group at CBPF. So you see, there were several people involved. That's also why we won. It's not because we are geniuses or anything, but because there was a lot of work involved with a lot of people. And these people, they worked hard between Christmas and New Year. So there was really people very hardworking, and okay, we got that. So now that we are able to measure things, we asked ourselves, okay, let's assume I don't have spectroscopy. I just have images. And will I be able to find a to test gravity only from images, not from spectroscopy? Everything that has been done up to now needs to have some spectroscopy of the source, okay? So we ran simulations again, more simulations, and assuming that we have 1,500 systems only analyzed in the images by this deep convolution neural network, and we measure the Einstein ring, which is the size of this ring, and the redshift of the galaxy of the lens. And we want to ask whether this data can be used to find gamma. And what we find in the simulations is that, again, if we assume that gamma equal 1, because on the simulation it was equal 1, I'm able to recover this value very precisely, okay? So we are aiming to make a totally automated test of gravity using Einstein ring and machine learning. And I hope in the very near future, we will be able to do this in the data, not only on the simulations. Okay, just to end, and according to my chronometer, I have 5 seconds, so I have to rush. After 30 years of the first discoveries of gravitational lensing, and after 100 years of general relativity, really gravitational lensing has transformed in a crucial observable for cosmology and astrophysics. The observables, you heard many times what they are, what they allow us to study, you also heard many times. And in particular, is like almost the only observable that is able to test gravity at the size of a galaxy, at the kiloparsec scales. Something that's very promising that I didn't mention today was also to test properties of dark matter at this scale, in particular to probe the substructure of the galaxies made of dark matter, which is also very peculiar from lensing, okay? So it's a very interdisciplinary field involving, from theory, from fundamental physics, like modifications of gravity, a lot of analysis, simulations, statistics. It's really a very interdisciplinary field. So it means that everyone maybe can contribute to this, even you, regardless if you are a physics student or from other fields. There's really a way where interdisciplinarity is very useful. We have already a lot of data, okay? So we have very big surveys like the Dark Energy Survey, like the Hypersuprime Cam, and many other surveys. And in the future, we'll have even more data with the Vera Rubin telescope, which is a 10-meter telescope in Chile, also with the Euclid and with the Roman space telescopes, and also with a lot of spectroscopy, like Mauna Kea Spectroscopic Explorer or DESI. We'll have lots of data. So now we have about 100 confirmed systems. We are growing to have like about 1,000 in a very short time. In a couple of years, we will have like 10,000 or maybe even 100,000 gravitational rings when we have these space telescopes running. So it's a field that has developed a lot, is very rich in the physics we can take, and there will be many years to come with a lot of new things. Okay? So thank you, and I'm open to questions. Gracias.
Muchísimas gracias, doctor. Ok, muchísimas gracias, doctor, por el tema muy interesante. Eh, Igualmente, nosotros estamos contentos de tener tanto usted como el doctor José Gómez acá presentes. En algún momento, en algún futuro, pues cuando ya la situación que actualmente nos encontramos viviendo pueda mejorar, pueda cambiar, podamos tener una segunda o tercera encuentro internacional donde ya podamos presentarlo de manera presencial. Entonces, están invitados de manera cordial para ese momento. Ok, voy a hacer la parte en inglés. Nuevamente, disculpen el pronunciación. Does anybody in the audience have a question? You can raise the hand or directly turn on the microphone. Eh,
Pueden preguntar en español, no hay ningún problema. Or you can ask in English, Portuguese, or
Hello.
other. Yes.
Hello, sir. It's me. My name is Raj Dash. Thank you for this nice talk. I'm from India. I'm a PhD student in Indian Statistical Institute, Kolkata. So my question was, if the in galaxy gravitational lensing, in the case of galaxy gravitational lensing, if the galaxy mass is spherically symmetric, totally spherically symmetric, then we can get then we will get a exactly Einstein ring, circular Einstein ring. It is possible?
Yes, yes. Actually, to get a complete ring, it suffices that the galaxy, there is something that we call a caustic, that when the galaxy is spherical, the caustic is a point. So it suffices that this point is inside the source to have a complete ring. But even if the galaxy has some ellipticity, if this caustic is small enough with respect to the source size, we'll have a perfect ring. So there are several situations where we can have a complete ring. We don't have to have like this perfect symmetry or perfect alignment. So that's why we see some of these systems in nature. Yeah.
Thank you very much, and thank you for your nice talk.
Thank you.
okay. Anyone to have a question? I see the. Okay.
Yeah, I have a question. Hi, Professor Martin. I'm David Camarena from PPG Cosmo. Maybe you remember
Hello.
me. We are in the same
Yes.
program. Thank you very much for the nice talk. Actually, I'm happy to see that people like you that lead the research in Brazil and other many countries are participating in this kind of events because I studied in Universidad del Callao. So my question is related with the fact that everyone is excited that we can test gravity in some sets using lensing, but what about, for example, test another things like, for example, cosmological principle? We can test if we live in an isotropy and homogeneity universe using lens. Is that not possible?
Right, it is possible. So actually, I mean, there's so much things that you can do with lensing that I can tell you, many things are possible. But there are some things that are done better with lensing than other things, okay? So for example, the homogeneity and isotropy, you can test with lensing because you can measure the cosmological distances, right? In the case, the angular diameter distance. So you can, the same redshift, if you have different distances in different directions in the sky, means that you don't have isotropy, for example. So it is possible. However, I don't think it's like the best probe to measure that. There are other probes like a CMB or other probes that you have much more data that are better for this application, homogeneity and isotropy. But I mean, it's interesting. And one thing that I think it was not studied enough, for example, is to take from the start, let's take a inhomogeneous model, like the popular Lemaitre-Thomson Bondi, okay? You could study lensing in this background that's very different from the standard. However, this was done, very few examples in the literature, and the things that I saw, some are really wrong. So there is room to study lensing in some alternative theories that I think was not explored too much. Yeah. And I'm glad that you studied at the University of Cajal. Good.
Yeah, and also, I don't know, maybe I missed something, but when you talk about this model to predict when you see the supernovae, after see the first one, you were referring to some astrophysical model, something related with cosmology, with gravity?
So We assume general relativity, and what we have to do is all these multiple images, they have to be mapped to the same source in the source plane. So we assume a model for the mass distribution, and what matters the most is not the cosmology, but is the mass distribution in the lens. So we make a model where the masses and the positions are free, and we minimize the model such that these images, they all correspond to the same source. So this is what we call the strong lensing analysis. It's a model of the mass distribution where we use also the cosmology, but really what matters more is the mass. So once we have a good model for the mass, then we can predict the time delays, and that's what was done. Still,
okay, thank you very much.
Yeah, since the model involves both the cosmology and the lens, you can also let the cosmology free, and we did this in one example. So you can use this to measure the cosmology once you have a good mass model. But the most important thing is the mass model.
Okay, we have two questions more. Clayson Amarike asked, are most equations in cosmology derived from any conservation particles? We have like conservation of energy, momentum, and so on, or they are built from data and scattering graphics due to instrumentation or measures? It seems like statistics and data are replacing maths.
Okay, I'm not sure they understood the whole question, but let's start from the beginning. So if we assume conservation of energy and momentum, yes, in the sense that the general relativity of the theory of general relativity, Einstein theory of gravity, it automatically has a local conservation of energy and momentum. Okay, so from this theory you can derive the local conservation of energy and momentum. So within general relativity, yes, is always the case. You mentioned about the particles and so on. You can make a statistical description of particles that is consistent with general relativity. So you can make I forgot the name now. Anyway, you can make a statistical physics which is relativistic, which incorporates general relativity and special relativity. So you can also treat these particles statistically. Well, I forgot the name now, but like in standard statistical physics. So you can write a statistical physics, a general relativistic statistical physics. There's no problem.
Okay, and the last question is from Sigal Lega. How black hole connected with the space-time curvature?
So the solution of a black hole emerges from the Einstein theory of gravitation. Is the simplest solution of general relativity because it's a point source of matter, so it has spherical symmetry and so on. And the black hole solution is an example where the space-time curvature matters. It gives all the basic properties of the black holes are due to the space-time curvature. So it's like black holes are an example of general relativity where space-time curvature is crucial.
Thank you so much, Doctor. And now to continue the program, now we will have the presentation of topic of interest in theoretical and applied physics. In room 1, we have David Choque with the talk Exacted Holographic RG Flows in the Extended Sugra. And the room 2, we have Ana Aguilar with the talk entitled Multifractal Analysis of ECG in Healthy Adults while they exercise. I put the links in the chat, and anyone to enter is to invite. We will meet at p.m. o'clock for the following lectures by the Dr. Odon Arestegui and Dr. Junior Silva. Thank you so much for the presentation, Doctor. Thank you so much, Dr. Jose Gomez. We see you in this room.
Okay, thanks so much for the invitation.
Hello,
Thanks for
sir.
the audience.
Can I ask a question again, if you allow us? One more question.
Yes.
Yes, sir. So Professor Martin, so whatever metric, means metric you have used or you have shown in the presentation, you have used the Newtonian gauged metric, which is there is a 1 plus 2 phi and 1 minus 2 psi term. So it is specially from that the spherical symmetric term e to the power I phi in a weak field consideration is simply 1 plus 2 phi. Am I right? So I mean to say, how can I know that this phi is a in weak field, this is a Newtonian potential from that technical aspect of view?
Right. So yeah. So this in the way that we wrote the metric, as you said, in the weak field limit, we would derive something analogous to the Poisson equation, where this G00 term will make the role of the phi. I don't think there's a factor of 2, but I may be, I have to look again, but I don't think there's a factor of 2 there, but there could be, okay? I can check this. Maybe there's a typo, but yes, it's the conformal Newtonian gauge. And, you know, we, for the perturbations that couple to matter in the linear regime, only the scalar part of them matters. So, but yes, it's like the standard weak field regime where we recover the Poisson equation. So the first term, the G00, the phi, will give you the Poisson equation, and the psi does not appear. Okay, it just shows up on the propagation of light, no geodesics.
Thank you very much again. Thank you, sir.
Thank you. So thanks everyone, and feel free to send questions by email and so on. It's a pleasure to be there. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye. Hasta luego, muchas gracias.
Hasta luego, doctor. Muchísimas gracias a usted también.
Muy bien, Jorge. Gracias.